potential game that we haven't really talked about last time. It is quite important concept because it can simplify, quite a few things that in a typical normal phone game. So I think it's very nice topic to really talk about. In fact, this is quite active research area as well, and we've been working on this topic. I in fact propose some of this new stuff on the subject. So if you are interested in further study on this potential game, that's I'm more than happy to have further conversation. So this potential game, let's looking at maybe before we actually go that, let's understand a bit about core node competition first. So remember, we explained the core node competition between two players. Suppose now we have I number of players or companies, right? And they can make a decision in terms of certain quantity QI. The I index is for each of the form they allow to choosing their own quantity. So this is considered their a continuous continuous action. And then they got the payoff function, which is a linear function respect to the total, or actually it's a quadratic, function respect to this quantity. And this the price on the market is the capital Q. The price of the in the common market is a function of total of quantities that generate from all the forms. And this function basically is a linear function that I written here. And so, but it could be other kind of function. And we started it was linear one. And then you can actually write it down this utility that this utility would depend on the quantity that I produced QI, but also on the quantity that from other forms or players. And then from this, different with this the core node formulation we did. In fact, we could formulate or define a function called phi. Okay, this phi is a global function that that depends on the the joint action, right? The joint action from all these forms. So you can think about this as sort of a product of all these quantities, and plus this sort of a the price and also the cost per per unit of the product that we can produce. So you could, if you define this global function phi, and they have quite nice kind of property. So you can find that in fact this difference between this phi function, okay, if you change, let's say my the quantity of the product that produced from let's say I form I, let's looking at this from form I perspective, and given any to a pair of this quantity that I can produce, and this difference between them, if the difference between them is larger than 0, and you can find that it's always true that the difference between the utility between these two different quantities are also larger than 0. So they got this quite nice kind of property, because then somehow this phi function specify the payoff, yet in a very simple form. When I say simple, is that you don't really need to have a UI function. In other words, that have one function for one player form, but you have just one global function to represent everything. At least the differences between the reward when you change one of this payoff. So formally, this function phi is if it satisfies this condition that we this condition, this ordinal condition, and we can call it ordinal potential. And if the game has that kind of function, right, identified, then we call this ordinal potential game. So in other words, that it's not all the game can find that ordinal potential, but it's there's a class of the game, in fact, would able to find that potential function. Therefore, we call it potential game. So if you have that kind of property, it's quite nice that you can actually draw the conclusion saying that this pure strategy equilibrium set would be the same as the set of the pure strategy strategy equilibrium set of the game created or defined by this phi function. In other words, that they would have one single reward for each of the form, and we created some kind of wouldn't call it a team game, but created some kind of game which just have one payoff function applied to everyone. And this is true because then you can actually looking at these. Suppose this Q, joint Q, is equilibrium, and it's not equilibrium. And if that's true, then you basically say any phi function, and if I using this sort of Q as input to that, because it's a Nash equilibrium. Because of this, suppose that this Q function, joint Q, would be the largest, would be the maximum point of this phi function. In other words, that if you're changing the value of this quantity, and then you would always find that they are become smaller, and then you could always say this Q, joint Q, is in the Nash equilibrium, right? Because of nobody want to deviate from it as a definition of Nash. So the sum definition here. So the strategy form gain is a potential function, is a potential gain, and if there's exists a phi, right, that tell you about something about this individual utility. And this phi, we call this potential function. And this potential function, the reason we call it potential function is because in physics that potential functions has this kind of form. This partial derivative of that would be same as this sort of derivative from this phi function. So you got a relationship between this individual utility and also this phi. You got this kind of nice property. That's why we call it potential game. So this again is more formal definition. I is a number of agents, and then SI is a state, and UI is basically utility of each of these I agent. Then the potential function is the particularly the ordinal potential function is that in terms of relationship between this utility is that to keep this ordinal relationship unchanged. So if I change my strategy, this if I find that my phi will decrease, I will also find my individual reward to the decrease as well. So this is the definition of this ordinal regression. You could have also exact potential function, is that instead of having this ordinal regression, ordinal relationship, you can actually have this exact difference, right? So this difference between phi if you change. So this is sort of a difference with phi change, then you would have, yeah, you would also have the exactly same change if you were using this individual utility to measure your payoff. And so let's look at an example just to make sure that you fully understand that. So we got this prisoner's dilemma. The prison dilemma, it is a potential game, is because instead of using like an individual utility payoff to represent the reward for each of the players, and we can just have one value, right? And then for player 1 and player 2, and in fact, if you have that representation, and it will be much simpler, right? And to see how this would change is that you can see, remember that remember that the potential game is that you can able to find this phi function that the ordinal keep the ordinal relationship. So if I change, let's say, from here to here, right, utility, to looking at what happens to the utility. So if I from here, this action changes to the action, basically the player one change from taking action 1 to here, and because of that, the reward actually reduced 1, right? The 1 minus 0 is actually reduced, and the difference is actually 1. So equally, if you're looking at here, is that if I move from this direction, right, basically player 1 changed their strategy from action 1, taking action 1 to taking action 2. And you're looking at this phi change is actually 4 minus 3 and also 1. So that means that the difference of this phi function is exactly the same as the difference of the individual utility function. You can also looking at this direction, right? This direction, you can looking at that is, okay, now the reward change is not about player 1 anymore. It's actually about player 2, because in this case, looking at the definition here is that I'm looking at this I, right, is basically for this guy. I'm looking at the action I take, but when I taking change my action, I'm only looking at the reward payoff for myself. So equally here, if I'm moving here from this joint action to this joint action, what actually changed is the player two's sort of action, they change. And when they change, we're obviously looking at their reward with the difference. So in this case, 9 minus 6 is actually 3. And if you're looking at here, 3 minus 0 is actually 3. So this phi really capture the differences of this payoff when they sort of move around by taking different action. And so this is sort of a definition of it. So you might want to ask, why do I need to have this, right? Why do I need to, looking at this potential function, whether there's a potential function for this game, what would I can get anything out of this? The answer is yes. Then you can really get a quite nice property of this if you can prove it is indeed a potential function. So one of the things is that if it's a finite ordinal potential game, like the theory we basically tell you that you will at least one pure strategy Nash equilibrium. Remember, when we have this finite game, as we defined previously, there's no guarantee you can have one pure strategy. There's no guarantee you can have that. But if you say, right, you are finite ordinal potential game, then you always guarantee you have at least one pure strategy. Okay, the reason, in fact, is quite simple. So the proof is the following: is that because you have this finite ordinal potential game, that means that this potential function would this relationship would hold. And then because this is finite, therefore think about this this phi function, and this is sort of action you got, right? This is sort of a joint action. Because of finite, therefore you have finite number of actions you can choose. Then this relationship holds is that you can in each of the sort of a difference, you update one of these action, and then you will eventually meet to this global maximum, because it's a finite number of moves that you can have in the finite ordinal potential, because you only have a finite number of actions. And eventually you will reach to the maximum of this ordinal potential function, and that's the pure strategy, because you don't want to deviate from it, right? And because of that, and you can actually say, think about that is, this difference there would be all for all the SI. And actually this are applied for all the I's, right? So because of that, and then that's also definition of the pure strategy large equilibrium. So that's this sort of a quite nice property. And just to give you an example, in the coordinate competition game, that if it's not necessarily say everything's linear, but if the cost is like any arbitrary function, then you can still define your potential function like this. So you can actually have a look to work it out this. Yeah. So let's looking at this some of this definition. Just try to really make sure everybody fully understand the concept. So we can define a path is that in the strategy space. Let's say that capital S is a strategy space, join the strategy space, and then the path is basically a sequence of this strategy vector. So this 0, 1 is actually concept, and then we basically make sure that two neighborhood strategy only different in one coordinates. So in other words, say as we sort of say previously demonstrate here, you can create this sort of a path. Say I go here, okay. If you're looking at that in the strategy space, I change the strategy from 1-1. This player 1 take action 1, player 2 take an action 1 from 2-1, right? Player 1 taking action 2, then player 2 taking action 1. So basically move only in that this two neighborhood sort of strategy profile. I only change the play for one of these players. And you can also do this, right? This is basically player 2 moves, and you do this, and you do back. So this is what we called path, okay? And improvement path is basically saying that in each step that I go further, I would always improve my utility. I will always improve my utility. And remember here is that when I say this path proof is that you can think about this. In this case, it's not, isn't it? It's actually reduced, just looking at this. And then looking at here, from 9 to 6, basically also reduced. From here to up, and then basically here you can see 6 to 9 is improved. And we will go back here again, is because it's a player 2 change their action. We're looking at 0 and 1 difference, and actually also is not improved. So I can actually draw this improvement curves, the error. so that we can have a much better understanding. So let's say in this case, I would have this kind of angle, right? Because this path is always goes to the high utility. From here to here is also this, right? Because from 0 to 1, this is from 0 to 1. And here, then is, if you're looking at this, is from 6 to 9, right? It's improving this direction. And if you look at that, is here as well. So it's basically 6 to 9 as well. So you basically say, if you're looking at the improvement path, is this. This is the improvement path. This is the improvement path, right? Because each of the steps, you can improve their respective utility. So here, you can think about this, that this S difference is in the cave coordinates. Okay, so that's the key, key thing in order to understand it. So it's not saying that I'm going to change my utility forever. It's really saying in this, path, I have this. I can see the utility increase, but only say for one of the users, for one of these. Sorry, not user, for one of the players. So you can think about this improvement paths sort of as a generated dynamic by myopic players. Think about this as sort of a, I think this myopically. In other words, I'm looking at the local improvement. We're starting here, then let's suppose my, joint strategy is this. I'm starting from here. Then if I want to improve it, I go either here, is basically say, okay, from player 2 perspective, I would able to improve my utility. And then from here to here is that from player 1's perspective, I would able to improve my sort of utility. So you can also go this way as well. So let's verify this. This is actually very interesting. Is that we're looking at this potential function, and we know that the maximum, the maximum value of this potential function, right? In this case, 4, which give us pure strategy. Okay, give us pure Nash equilibrium. Sorry, pure Nash equilibriums. The pure Nash equilibrium. Then, and you can look at this sort of improvement path. They all towards to this. Okay, they all towards to this. So again, I think there's also this proposition is that in every finite and ordinal potential game, every improvement path is finite. Okay, think about this. You got this pure strategy, which is a maximum of this ordinal, of this phi function. And then because you only allow to have, finite number of configurations, if you like, in terms of this, state. Therefore, they might wish to, they might finite step, they might reach to this maximal. Okay, once you reach to this maximal, you basically stopped. Because when you go to the maximal, there's no way you can improve further. Therefore, this improved path would terminate. So, in other words, that this every improvement path is finite in this, finite ordinal potential game. And when they terminate, they reach to the maximum, points of this potential function. And in other words, they also converge to the equilibrium set. So what I say is that there's an converge to the equilibrium set. I didn't say the converge to the equilibrium, because it could potentially have a multiple equilibria. So the nice thing of this is that so we're not gonna prove this theorem, but I can actually refer to the original paper by Shapley. So this called this nice sort of a property is that you can actually define this finite path, And this finite path is eventually when you go back to the original, let's say you reach to the circle, and when you reach to the circle, what I try to say is this: is that you could think about this as you keep doing this, not necessarily improvement path, but say you go this circle. When you go back, and the improvement would be 0, isn't it? So you go here, when you go here, go down, down, go here, and then you would get the same. You would get the same sort of a utility or same potential value. So that's what this theory is trying to say. So in other words, that you could using this to verify whether it is a potential function. So this I means that if you have a circle and reach the destination, then you wouldn't really see any difference between them. Okay, so that's this gamma path. It means gamma path saying that from the starting point and go to this sort of path, right? Some improvement, some sort of goes down, and as long as this S0 Sn is same, you go back to the origin, then this value of it would be 0, right? The improvement would be 0. So which is intuitively correct, right? Because just looking at this example, you're starting from here, you improve you start from here, you go down a bit, and then you improve it and improve again. So when you're looking at the difference between them, eventually it's the same. So that's this nice property, and actually they will show this simple closed path, its length is 4, right? Because it's quite understandable. You just keep the other. Suppose you have many agents, it's fine, but you just keep the 2 agents, and you just keep these 2 agents, 2 actions. Therefore, this smallest simple closed path is basically 4 length is like basically 4. So just like this example. Oh, this is not really convert PDF nicely. So here, the same as before, you can actually to see that you would have this finite number of improvement until you reach to the maximum, right? You can try this. Indeed, it's in the case. So here is a question that I wanted to ask. What in this 4 case, what are the potential games? What are not potential game? You can have a think, and then if you know the answer, yeah, please go ahead. Based on the discussion we got, you could write it down your potential function if you somehow derive it. Oh, by the way, when I say how to obtain this potential function is non-trivial, is that in the general setting. But of course, in this ordinal potential game, or this exactly potential game, that you have this normal form kind of reward table, then obviously you can derive, you can obtain it. The answer, yes. So match penny, it is not potential game, whereas the others, they are. So let's have a look. Okay, so let's look at the battle of sex that we haven't really seen. So we start with this. If you go up for this path, and because in this case the player 1 changed their player change their payoff. So let me, yeah. So basically you got this 2 minus. Let's write it down this here, and you got this 0 0, and here you've got this improvement, which is 1. Did I write wrong? Okay. Oh, sorry. So yes, so here that's starting from 0, 0, and then when you sort of have this path to the 1, 1, that in that case 2, 2, 1. In this case, you improve the player 1 improved their reward, right, by 2. So equally from 0, 0, start from here, you can see that is an improved path is because the player 2 also improve their payoff by 1. So let's put this. And here, from 0, 0 to downwards is that you could looking at it's player 1 change their strategy, isn't it? So from this case, you can also see if you go down, also improved. And same case that from 0, 0 to 1, 2 is that the player 2 improve their path. So from here you can see that this improvement path would has a terminate a few steps, like finite steps, and which to these the equilibrium, right? These one of the equilibrium, right? Because it will reach to the equilibrium set. And so same case for here as well. So then some of this equilibrium is basically could be potentially a global ones, right, like this, or could it be the local ones, like this. So not necessary to be global. And the multiple of that, then you can have the multiple equilibria. Okay. And so then the last question, are the potential function unique? I think people ask that question about, do we have an infinite number of potential functions? I think this can be answered by, you can always add a value to a constant value to a potential function. That they wouldn't change anything, wouldn't it? Because you could looking at these different functions. And therefore, by doing this, you have a infinite number of these potential functions. Okay, and if you're looking at this, it's actually quite different. It's you can looking at this. You can always have the improvement. Keep circling around, So it doesn't really fulfill this these properties that we just mentioned, right? If you have the circling of any circle, let's say in this case 4 steps, and this sort of improvement should be 0, but actually you can see that keep running, keep improving that. So I think if you look at that as this, is it doesn't fit to the characteristics of this potential game. So therefore, match pen is not.